Hello and welcome to Physics Tutorials with Uviemine Collins or no Brakbeya. You can simply call me Mr. Collins. In this video, we shall be carrying out an experiment to measure the focal length of a converging lens. We are provided with a lens and a lens holder. You can see here that the lens is suspended by the lens holder, alright? Or you can see the lens holder holds the lens, and then we'll have a screen. Alright, we're provided with a screen and also with a raybox which encloses an electric bulb. In the course of this experiment, we'll connect this bulb to a power supply. Also, we are provided with a meter rule. The instruction says measure and record the size A0 of the illuminated object. I'll tell us what the object is in a moment. And then we're told to place the object O and the screen S on opposite sides of the converging lens L. What does that mean? Here we have the screen S, we have the lens L, which is suspended by the lens holder, and then we have our ray box. Now, where is the object? Behind the surface of this ray box are metal threads that can be seen through a hole here. Alright, those metal threads are the objects. Okay, they are considered as the objects. Okay, so we are told to measure and record the size A0 of the illuminated object. That simply means measure the diameter of this hole. Okay, now we're told next to set the distance u between the objects and the lens to be 30 centimeters. That's a function of u here. Okay, we'll set it to 30 centimeters. Next, we're told to adjust the screen until a sharp image of the illuminated object is obtained on the screen. What does that mean? When we connect the bulb here to a power supply, it will incident light on the object. Don't forget, we said the objects are threads, alright? Metallic threads that can be seen through the hole here. Okay, now that light will be focused on the screen by the converging lens. Okay, so we'll have an image of the objects on the screen. So we'll see the metallic threads in this form displaying on the screen. Alright, now the diameter of this hole here is our A0, while the diameter of the image formed on the screen will be called A. Okay, and so we are told to measure and record the size A of the image, alright, which I've just told us, and then to evaluate M, which is equal to A over A0, where of course A is the diameter of the object, alright, which is the diameter of the hole of the ray box, and our A is the diameter of the image formed on the screen. And then we're told as well to measure M inverse. Of course, if M is A over A0, it implies that M inverse is A0 over A. Further instruction says we're to repeat the procedure for 4 other values of U, which are 35, 40, 45, and 50 centimeters respectively. Then we're told to tabulate our readings. Then it says plot a graph of M inverse on the vertical axis against U on the horizontal axis. Next, we're told to find the slope of the graph and then to determine the value of U for which M inverse is 0. And then lastly, we're told to use our graph to determine the value of M for which U equals 37 centimeters. We shall carry out these tasks in this video. Now, our first instruction says measure and record the size A0 of the illuminated object. For us, the objects here are metallic wires embedded inside the ray box. Okay, so how do we measure A0? A0 is simply the diameter of this ray box. Of the hole. So I would place this meter rule to measure the diameter of the hole. It appears to me like it is 2.3. Alright, so the value of our A0 is 2.3. 2.3 centimeters. We are told to place the object O and the screen. So this is the object, which is actually our raybox, and the screen. We are told to place them on opposite side of our converging lens. All right, this is the lens held by a lens holder. All right, so this is our screen, this is a meter roll, and this is our raybox, of which inside it contains the object. Next thing it says, set up the distance U between the object and the lens to be 30 centimeters, and we have done that. If you can read off the value on this meter roll, you'll discover that it is 30 centimeters. So from the object to the lens is 30 centimeters. Then we are told to adjust the screen until the sharp image is formed. Now you can see we have a blurry image. I'll keep adjusting. This seems to get more blurry, so I'll take it back, and it appears to be getting sharp. If I take it beyond this point, it's blurry again. So this, let's see, beautiful. This is our sharp image. Next thing, we are told to measure and record the size of the image. So again, I'll come here to measure the diameter of this image. If I do that, the value I'm getting here is 2.1. All right, 2.1 centimeters. All right, so next it says we should adjust this till this is 35. If we do that, we're told again to adjust this. You can see just slight movement backward, and you have your second sharp image. Okay, so here again we're told to measure this. As we take it further, the diameter gets smaller. This is 1.6, 1.6. Okay, and then we'll move it to 40. So just on and on like that. For this video, we'll take it to 40, and then I'll show you the values of the others. So I'll move it backward slightly again, and then you see the sharp image. All right, the more we increase the length U, the smaller the diameter of the image formed. Okay, this is our sharp image. Backward it's blurry, forward it's blurry. So we'll look for the place where we have a perfect sharp image. All right, I would work with this. It looks very much crispy, and then I would measure this. This appears to be 1.123. I would call this 1.3. All right, so on and on like that. We'll keep adjusting the distance U till we get to 50 centimeters. Then all through we'll measure the diameter of the image formed, and that'll be the value of A. All right. So, having performed these experiments, these are the values we obtained. So this is our table of values. First of all, we measured the value of A0 as 2.30 centimeters. All right, and then we went ahead to measure the values of U, and then to get the corresponding value of A. Okay, and then from that we were told to obtain M, which is A over A0. Okay, so for the first one here we have 2.10 as the value of A. We divide that by 2.30, which is the value of A0, and that gave us our 0.913 here. Then the inverse of that gives us our M inverse, which is 1.095. There are two ways to do this. It's either you find the inverse of 0.913, or you just go ahead to say if M is A over A0, it implies that M inverse is A0 over A. All right, and that will give us this value here. We did that for all the values of U and A, and we got the values of M and M inverse. All right, now two things I would like us to take note of on this table of value. One is the fact that our measured values are recorded to 2 decimal places. All right, we measured U and we measured A, and also A0. All right, you can see they're all expressed in 2 dp. All right, in 2 decimal places. Our M and M inverse were estimated from A over A naught and A naught over A respectively. As such, they are called measured values, alright? Measured values are to be expressed in 3 decimal places, and that's why we have them displayed in 3 decimal places. The second thing I'd like for us to take note of on this table is the fact that our units are expressed beside the quantity. Now, we know that the standard unit for length is meters. However, the measuring instrument we used is calibrated in centimeters. As such, we have our U in centimeters and also A in centimeters. Our M and M inverse have no units. Why? The units of A would divide that of A naught. Our A is in centimeters, our A naught is in centimeters. They will both cancel out, leaving our M without a unit. The same thing applies with M inverse. Alright, they both have no units. Now, we're told to plot a graph of M inverse on the vertical axis against U on the horizontal axis. Let us choose a suitable scale for this graph. How do we do that? I have been able to outline steps that can guide our choice of a scale. The first step is to find the highest value of the quantity to be plotted. Now, let us first focus on the horizontal axis. We are plotting U on that axis, and the highest value here is 50.00. Next, to get a suitable scale, we can as well go ahead and count the number of boxes along the axis of interest, knowing fully well that each box, or each big box rather, corresponds to 1 cm or 2 cm. For the graph we shall be making use of in this video, each big box corresponds to 2 centimeters, and along the x-axis we have 10 big boxes. Okay, I'll soon display the graph for us to see. The next step says we are to divide the highest number, which is 50, by the number of big boxes. Now, we counted that to be 10. I'll soon show us. So we'll have 50 divided by 10, and that will give us 5. It means along the x-axis, each big box, which is 2 centimeters, would correspond to 5 units. Alright, now let us do the same thing for the y-axis, that's the vertical axis. The highest value there is 2.556, and on the graph which we shall use, there are 14 big boxes along the vertical axis. If we divide out 2.556 by 14, 2.556 divided by 14, this will give us 0.1826 approximately, right? But we cannot use this value as a scale. Okay, what do? That's where the fourth step comes in. It says round up the answer to the nearest appropriate greater number. If I'm to round this up, I would round it up to 0.2. Alright, and as such, along the vertical axis, each big box, which is 2 centimeters, would correspond to 0.2 units. Alright, now let us go ahead and apply that. Now these are the values we're going to plot. We're plotting our M inverse on the vertical axis against U on the horizontal axis, and this is the scale we have deemed to be suitable for this graph. Okay, let us go ahead and calibrate our graph. So the first thing you should take note of here is the title of your graph. It must be displayed. Okay, you must write out the title. This is a graph of M inverse versus U in centimeters. Of course, our M inverse has no unit, but our U is in centimeters. The second thing you must take note of is the fact that we have labeled our graph. Okay, on the vertical we have M inverse, and on the horizontal, if you check the bottom right, we have U. Okay, so let us put the values there. Okay, so we have U. Next up, we're going to find out what each small box stands for. We have said each big box along the horizontal axis represents 5 units. How about the small box? Now there are 10 small boxes within each big box. It means that if the spacing, or if the value between 0 here and this is 5, if we have 5 units for each big box, it means each small box would be 5 divided by 10, because there are 10 small boxes between 0 and 5. Okay, so 5 divided by 10 would give us 0.5. As such, the first box here is 0.5, next is 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, 4.0, 4.5, and then 5.0. Okay, so each small box along our horizontal axis corresponds to 0.5 units. All right, we wouldn't write that as a scale, but we must know that when we are finding our points on the graph. Now, let us go to the vertical axis. What will each small box stand for? Again, there are 10 small boxes between 0 and 0.2 here. It implies that each small box, therefore, is 0.2 divided by 10, and that gives us 0.02. So this is 0.02, 0.04, 0.06, 0.08, 0.01. All right, sorry, let's go through them again. 0.02, 0.04, 0.06, 0.08, and then we have 0.1. All right, or 0.10, the same thing. And then we go up here, we have 0.12, 0.14, 0.16, 0.18, and then we have 0.2. All right, so along the vertical axis, each small box represents 0.02 units. All right, now let's go on from there to identify our first point, our first reading. Okay, we have said our M inverse will be plotted on the vertical and then our U on the horizontal. So we can spot out 30 there. How about 1.095? To get that, we'll come to 1 here. This is 1. The next is 1.02, 1.04, this 0.02, 0.04, 0.06, 0.08, and this is 1.1. All right, we have 1.1. Now, the value 1.095 is close to 1.1, all right? It is closer to 1.1 than to 1.08. Okay, so we shall make use of that point. If we trace it to meet 30, it means we would have this as our point. Okay, we go on to the next value. We have 1.44. So this is 1.4. The next is 1.42. The next should be 1.44. So we trace that to 35 and we'll get that point. Okay, we go on to 1.77. For that we have 1.6. This is 1.62, 1.64, 1.68. This is 1.7, 1.72, 1.74, 1.76, 1.78. Now 1.77 lies between 1.76 and 1.78. For this graph, I would make use of 1.78 because I had earlier worked with 1.1 when I had a value of 1.095. Okay, I used the higher value of 1.1 as against 1.08. So I'll stick with that all through the graph. Okay, if I have a choice, if I have to make a choice, I would use the higher value. So here I have 1.77. I would work with 1.8 instead of 1.6. With that, I'll have this as my point. Okay, I'll then go further and get other points. Here is our next point from 45 centimeters of U, and then for 50 centimeters we have that point, which corresponds to 2.56. Okay, the next thing for us to do is to draw our line of best fit. Okay, this is our line of best fit. In previous videos I have taught us how to get our line of best fit. We can see here that the values that are not on the line are 3, all right, 2 to the left and 1 to the right, but then they're very, very close. The last value appears to be an outliner. Okay, the last value here appears to be an outliner, but then the others are very, very close to the line of best fit. Okay, next we are told to find our slope. For the slope, we draw lines that we can read off. We draw a triangle. We draw a right angle triangle that has its hypotenuse as the line of best fit. Okay, this is what we have drawn. Okay, here we have the line. I'll try to adjust this, but let us read it off on the x-axis and the y-axis. Here we can read off the values. Along the vertical we have 2.06. okay, 2.06. The next one can easily be spotted as 0.6, okay, and then along the horizontal we have 20.5 as this value. Don't forget we said each small box stands for 0.5, okay, so if this big box here is 20, the next should be 20.5, and then for the other one there we should have 45.5. So these are the values we shall make use of to obtain our slope. Don't forget our slope is the change in the quantity on the y-axis over the change in the quantity on the x-axis. Okay, on our y-axis we have m inverse, and then on our x-axis we have u. So our slope is delta m inverse over delta u. The values we found were 2.06 minus 0.6, and then over 45.5 minus 20.5. If we play with that, we would have 0.0584 per centimeters. Do not forget to always put the SI unit, or the unit rather, of your slope. Our m inverse had no unit, but our u was in centimeters. It means we would have 1 over centimeters for the unit, which is equivalent to per centimeter. Alright? Whichever way you choose to write it, either as this or as this, you would still be correct. Okay, next we're told to obtain the value, or to locate the value of u at which m inverse is 0. So what does this mean? I'll change my pen here so I can explain to us properly. We're told to find the value of u when m inverse is equal to 0. Now, there is a physical interpretation to the value of u at the point when m inverse is equal to 0, and we should know what it means. Now, so far so good. Let us see what we have done. We have objects such that we measure the height of the object to be a0. We have our length, and then the distance between the object and the lens is u. That's the object distance. And then we have a screen, or we had a screen here, and then an image was produced such that the distance between the lens and the image is v, and then we're told to measure the height of the image. Now, don't forget we're told also to find m such that m is a over a0. What is the physical interpretation of m? M is simply the magnification. Why? It is image height over object height. Okay, so m here stands for magnification. Now we are told to find the value of u when m inverse is 0. Now when m inverse is 0, it implies that m is infinity. Why? Because 1 over infinity is equal to 0. Okay, so since 1 over infinity is 0, and we're told that at that point 1 over m is 0, it means at that point m is infinity. Now, when does a converging lens produce infinite magnification? It does that when the object is placed at the focal length of the lens, which means when the object distance u is equal to the focal length f, then we'll have infinite magnification, which means m will be equal to infinity, and as such m inverse will be equal to 0. It therefore implies that the value of u that we obtain when m inverse is 0 is the focal length of the lens. Okay, so the significance of u when m inverse is 0 is that u at that point is the focal length of the lens. So how do we do that for the graph that we have in front of us? Let us go back to our graph. This is our graph. Alright, now the value of m inverse, or the value of u rather, when m inverse is 0, how do we get that? This is our m inverse here. Okay, we trace it down to 0. It is 0 at this point here. Okay, now what is the value of u? We come along the x-axis and we find the value of u. the value of u here appears to be exactly 10.0 centimeters. Okay, this implies that at m inverse equals 0, our u is equal to 10.0 centimeters. Now, just so that you know, the value of u should correspond to the focal length of the lens you have used. Okay, this implies that I used a converging lens that has a focal length of 10.0 centimeters. Okay, next up we're told to identify the value of m inverse when u is 37 centimeters. All right, how do we do that? We try to identify 37 centimeters of u. Okay, so this is 35, this is 35.5, this is 36, this is 36.5, and then this is 37. Okay, so that's our 37 right there. And then the next thing is to read off that value through the line of best fit on the vertical axis. Okay, we do this. We trace it to the vertical axis through the line of best fit. Okay, if we do that, what is the value here? Let us read it off. If this is 1.6, this will be 1.58, and then below that should be 1.56. Okay, so that becomes the value. It implies therefore that at u equals 37 centimeters, we have the m inverse is 1.56, and as such, m should be 1 divided by 1.56, which gives us 0.64. So we have been able to accomplish every task that was set for us at the beginning of this video for this experiment. Alright, so if you have enjoyed this video, I would encourage you to subscribe to it so that you can be notified when other videos are released. Okay, I subscribe to the idea that you should subscribe to this channel. Okay, and then also you can like it, you can share it with your friends. Alright, thanks for watching and see you in our next video.